are 40 billion Earth-sized worlds sitting inside the habitable zones of our galaxy. 40 billion locations where liquid water might collect, where chemistry might eventually become biology. 6.5 decades of hunting every star we can reach has returned a single answer: 0. We are going to follow that 0 through 76 years of inquiry. Starting from a lunch table in New Mexico, moving through a signal that blazed for 72 seconds and never returned, all the way to the economists and physicists who believe they understand what is extinguishing every civilization before it grows loud enough for anyone to detect. Along the way, you will witness telescopes bulldozed for golf courses, a Russian astronomer who beamed humanity's coordinates into the cosmos without asking permission, and 2 papers released in the last 2 years that positioned the Great Filter directly in our path. In March of 2020, after 21 years of uninterrupted operation, SETI at home quietly powered down. The I project had harnessed millions of volunteer computers across the globe to comb through radio telescope data, hunting for patterns that might suggest an intelligent signal originating somewhere beyond our planet. Across those 2 decades, those machines worked through 12 billion candidate signals. 12 billion. Every last one proved to be noise, not a single confirmed transmission from another world. The final tally after all that time and all that computational effort was 0. That figure deserves a pause. 65 years of formal searching, beginning with one radio telescope in West Virginia in 1960 and extending through some of the most powerful instruments our civilization has ever assembled. Thousands of researchers across dozens of nations, hundreds of millions of dollars in funding, largely from private sources, because the United States federal government stopped financing this work in 1993, and the answer, as of early 2026, remains 0. This is not a shortfall of effort. The Breakthrough Listen initiative alone has examined approximately 1 million nearby stars and gathered more than 2 petabytes of raw data. The cosmic system operating on the Very Large Array recorded over 950,000 distinct sky fields during its first 11 months of operation. The Murchison Wide Field Array canvassed 2,800 entire galaxies. Every search, every instrument, every frequency range delivered the same verdict: nothing. The number of locations where life might plausibly exist keeps rising at the same time. As of early 2026, astronomers have verified more than 6,000 exoplanets. Statistical frameworks built on data from the Kepler Space Telescope place roughly 40 billion Earth-sized planets within the habitable zones of their stars in the Milky Way alone. 40 billion candidate homes for biology in just one galaxy. And the observable universe contains no fewer than 2 trillion galaxies. Consider that ratio: 40 billion potential Earths in our galaxy. 0 signals found. If you distributed those 40 billion worlds evenly across the Milky Way's disk, any one of them would sit within about 2 light-years of another. That density exceeds the typical separation between most stars. Geography is not the obstacle. So, the most expensive, most exhaustive search in the history of our species has yielded a single data point, and that data point is 0. Many people treat this as a non-result, a shrug, a void of information. It is precisely the opposite. 0 is a measurement. It is the most consequential measurement in the entire history of the hunt for extraterrestrial intelligence. 6 decades of accumulated null findings fed through statistical models now constrain the number of detectable technological societies in the Milky Way to fewer than 1 to 5 per century. That is not speculation. That is what the numbers require. The question driving this investigation is simple to pose and extraordinarily difficult to resolve. If life gets started easily and planets are everywhere, what is eliminating every civilization before it can make itself known to us? Something is sifting them out. Something is preventing the galaxy from saturating itself with transmissions and spacecraft and unmistakable signs of construction. The universe has had 13.6 billion years to generate neighbors. It produced us. As far as every instrument we have tells us, it produced nobody else. That is the foundation. The silence is not empty. It carries information, and the information is troubling. To grasp why, you have to travel back to a cafeteria in New Mexico, a summer afternoon in 1950, and a question posed over lunch that remains unanswered today. The Los Alamos National Laboratory, summer of 1950. 4 physicists are strolling toward the midday meal. Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski. The conversation is relaxed. Someone mentions a recent New Yorker cartoon lampooning flying saucers. There had been a run of UFO sightings making newspaper headlines, and the 4 physicists tease each other about them as they settle into their seats. Then, midway through the conversation, Fermi interrupts with a question that stills the table. Where is everybody? The other 3 know at once what he is asking. Fermi was posing a mathematical problem. The Milky Way harbors somewhere between 200 billion and 400 billion stars. It is roughly 13.6 billion years old. A technological civilization expanding at merely 1% of the speed of light, a rate far below anything requiring exotic propulsion, could traverse the entire galaxy in somewhere between 10 and 100 million years. That span sounds enormous until you compare it to the age of the galaxy. 100 million years is less than 1% of the Milky Way's total existence. There has been adequate time for this to unfold thousands of times over. Fermi scratched out back of the envelope estimates right there at the table. The numbers were not borderline. They were not open to much interpretation. Even under cautious assumptions about how often stars carry planets, how reliably chemistry produces life, and how long civilizations endure, the galaxy should be saturated with evidence of intelligent activity. Ships, signals, engineering at scales visible across stellar distances. There should be something registering somewhere. There was nothing. The question struck differently from an ordinary scientific puzzle. Most problems in physics have a clear line of attack. You design an instrument. You conduct an experiment. You record the results. But Fermi's question pointed at an absence, and absences resist study. You cannot train a telescope on silence and extract an explanation from it. The question hung in the air unresolved through the rest of lunch. It sat unresolved for the rest of that decade. Michael Hart gave the argument its rigorous form in a 1975 paper. If interstellar travel is possible even at modest velocities, and if civilizations emerge, with any frequency, the galaxy should already be occupied from one end to the other. The fact that it plainly is not demands an explanation. Every proposed answer to that question now bears Fermi's name, even though he never committed the argument to paper himself. He only asked, and no one could respond. To appreciate the timescale issue, consider this framing. Compress the entire history of the Milky Way into one calendar year, with the Big Bang falling on January 1st and today on December 31st. 100 million years corresponds to roughly 2.5 days. A colonization wave advancing at 1% of light speed would cross the galaxy over a long weekend. The galaxy has experienced the equivalent of all 365 days. Time was not in short supply. Space was not in short supply. Raw materials were not in short supply. Every generation of stars forged heavier elements, enriching the next generation with more elaborate chemistry. Fermi's question was not rhetorical. He expected someone to identify the error in the reasoning. Nobody did. And for 10 years after that lunch, the question sat dormant, because the tools to pursue it did not yet exist. Then one man decided to stop debating and start listening. April 8, 1960. A 29-year-old astronomer named Frank Drake swings an 85-foot radio telescope at Green Bank, West Virginia, toward two nearby stars, Tau Ceti and Epsilon Eridani. He dials in 1,420 megahertz, the emission frequency of neutral hydrogen, the most plentiful element in existence. Giuseppe Cocconi and Philip Morrison had championed this frequency in a 1959 paper in Nature, arguing it was the natural channel for communication across interstellar space. Any technological species would be familiar with the hydrogen line. It was the self-evident place to listen. Drake named the effort Project Ozma after the Queen of the Land of Oz. Over roughly 150 hours, he listened. At one moment, a strong pulsing signal appeared and the entire team went rigid. It turned out to originate from a high-altitude aircraft. After that false alarm, the remaining hours produced only silence. Ozma found nothing, but Project Ozma carried within it an assumption that would require decades to correct. Drake and nearly everyone in the field believed planets were a rarity. When Drake convened a gathering at the Green Bank in November of 1961 to structure the search more formally, 10 participants, Carl Sagan among them, worked through what would become known as the Drake equation. It was not truly an equation in any rigorous mathematical sense. It was an accounting system, a method for organizing ignorance into legible categories. You multiply the rate of star formation by the fraction of those stars that develop planets, by the fraction of those planets capable of harboring life, by the fraction where life genuinely appears, by the fraction where intelligence follows, by the fraction that build a technology we could detect, and, finally, by the average lifespan of such civilizations. The second variable, the fraction of stars with planets, was assigned the symbol Fp. Drake and his colleagues set it at 0.2, 1 in 5. It was an educated guess, and it felt optimistic at the time. Many astronomers suspected planetary formation might demand exceptional circumstances. They were wrong by a factor of 5. Between 2009 and 2018, NASA's Kepler Space Telescope fixed its gaze on roughly 150,000 stars and watched for the faint dimmings produced when orbiting worlds crossed in front of them. Kepler verified 2,783 exoplanets. The statistical analysis that followed overturned the foundational assumption. Virtually every star in the Milky Way harbors at least one planet. The parameter Fp climbed to effectively 1.0. Every star. To grasp what this does to the arithmetic, take the Milky Way's estimated 200 to 400 billion stars and substitute 1 for 0.2. The planetary census jumped by a factor of 5 overnight. Further examination of Kepler results placed roughly 40 billion Earth-sized planets within the habitable zones of their host stars across our galaxy alone. 40 billion worlds where liquid water could sit on a surface and chemistry could proceed toward complexity. That comes to approximately 5 such worlds for every living human being on Earth today. This was supposed to be cause for celebration. More planets means more opportunities for life, more chances for civilizations, more occasions for contact. Instead, it made the silence catastrophically harder to accept. If the real estate was always this generous, the question was no longer whether enough planets existed. The question became, with 40 billion plausible homes, why is the neighborhood empty? Every new exoplanet confirmed tightened the paradox another notch. The galaxy was not deficient in places where life could begin. Something else was suppressing it. And 7 years after Ozma, a graduate student stumbled onto something that everyone initially thought had to be the answer they were waiting for. 1967. Jocelyn Bell Burnell, a graduate student at Cambridge, is working through data from a radio telescope constructed to observe quasars. She spots a signal, a fast metronomic pulse arriving every 1.337 seconds. Nothing in nature was known to repeat with that precision. Her research group labels the source LGM1, Little Green Men. The joke is only half a joke. For weeks, the possibility that the signal is artificial stays on the table. Bell Burnell and her supervisor Anthony Hewish treat it as a genuine candidate. Then a second pulsating source appears in a separate region of sky. Then a third. The answer turns out to be rotating neutron stars, the crushed remnants of dead suns spinning at astonishing rates and sweeping narrow beams of radio energy across space like lighthouse beacons. The signals are wholly natural. They are named pulsars. The episode mattered for 2 distinct reasons. It showed that the universe manufactures phenomena that imitate intelligence with uncomfortable fidelity. A perfectly regular pulse cycling without deviation looks designed. It was not. Nature can be deceivingly orderly. And that lesson would resurface repeatedly across the decades that followed, because the history of searching for extraterrestrial intelligence is fundamentally a history of mistaking pattern for intention. 10 years after LGM-1, the reverse occurred. On August 15, 1977, Jerry Amon, a volunteer astronomer collaborating with Ohio State University's Big Ear radio telescope, was reviewing data printouts the day after the observation. Big Ear was a flat reflector telescope that surveyed strips of sky as Earth's rotation carried them through its fixed beam. The output emerged on continuous fanfold paper, columns of alphanumeric characters encoding signal strength at varying frequencies. One sequence leapt off the page. At precisely 1,420.726 MHz, the hydrogen line, a signal appeared that registered roughly 30 times above the background noise of space. The peak intensity surpassed 250 Janskys. It persisted for 72 seconds, which was exactly the interval any celestial source would occupy in Big Ear's beam as our planet rotated beneath it. The signal behaved precisely as an extraterrestrial transmission was expected to behave. Amon circled the character string 6EQUJ5 and wrote a single word in red ink in the margin. Wow. To give 250 Janskys physical meaning, picture the contrast between a whisper and a shout in a silent room. The cosmic background radiation at that frequency is the whisper. The wow signal was someone bellowing directly into a microphone at exactly the frequency that Cocconi and Morrison had identified in 1959 as the Universal Interstellar Communication Channel. The signal never came back. Eman and colleagues aimed Big Ear at the same section of sky hundreds of times across the years that followed. Nothing. Other telescopes examined the same coordinates. Nothing. The source lay in the I direction of the constellation Sagittarius, toward a patch of sky containing no notable star or catalogued object. For the next 4 decades, the WOW signal stood as the single most compelling candidate for an extraterrestrial transmission in the entire history of SETI. One burst, 72 seconds, then silence. It was LGM-1 inverted in every respect. The pulsars repeated and turned out to be natural. The WOW signal arrived once and resisted natural explanation. What became of it, and of the telescope that captured it, constitutes one of the more peculiar chapters in the annals of science. The Big Ear radio telescope operated from 1963 until it was torn down sometime between 1997 and 1998. The land in Delaware, Ohio, was purchased by a real estate developer. A golf course was constructed on the site. The instrument that recorded humanity's most persuasive candidate for contact with another civilization was dismantled, so that people could play 18 holes where it once listened to the sky. If you stand on that ground today, nothing marks what once stood there. The WOW signal, through all of this, remained without explanation. Dozens of hypotheses circulated over the following decades. Satellite interference, a classified defense transmission, an equipment artifact. None held. The frequency was too precise, the behavior too consistent with a deep space source, the intensity too elevated for any recognized terrestrial or orbital mechanism to account for. Then, in 2017, Antonio Paris, an astronomer at St. Petersburg College, put forward a resolution that appeared to settle the question. 2 comets catalogued as 266P, Christensen, and P/2008Y2 had been positioned in the general vicinity of Big Ear's beam on the night of August 15, 1977. Paris argued that hydrogen clouds enveloping these comets could generate emission at 1,420 megahertz, reproducing the signal Eman had recorded. Comets do carry hydrogen. The frequency fit. A number of news organizations reported the mystery as closed. The explanation felt tidy. It furnished the WOW signal with a natural origin. It gave the broader scientific community permission to move on. For a few years, many did. The comet hypothesis worked its way into popular science articles and documentary videos as the accepted verdict. Except the problems were apparent from the outset. Other researchers noted that the comets in question were not actually located in the correct feed horn beam position on that date. Big Ear used 2 feed horns, and the geometry placed neither comet where the signal had been recorded. More fundamentally, comets radiate at 1,420 megahertz at extraordinarily low intensities. The output a hydrogen cloud surrounding a modest comet can produce is many orders of magnitude below 250 Janskis. The suggestion is comparable to proposing that a birthday candle ignited a forest fire visible from space. The magnitudes were incompatible. For context, the entire WOW signal delivered more radio energy to Big Ear's receiver in 72 seconds than any documented comet has ever produced across all of recorded radio observation. A comet capable of generating that signal would need a hydrogen envelope roughly the volume of a small planet, emitting in a manner no observed comet has ever displayed. The refutation of the comet hypothesis unfolded gradually. Several researchers published critiques between 2017 and 2018, but the pushback received far less coverage than the original proposal. In popular consciousness, the comet answer persisted. It was clean. It was satisfying. It allowed people to stop asking. Then, in 2025, a research team decided to return to the source material, the actual physical printouts from Big Ear's observing run in August of 1977. 75,000 pages of dot matrix output that had been sitting in archives for nearly half a century. No one had conducted a thorough systematic reanalysis of the original data in decades. The results destroyed the comet explanation and replaced it with something that no one had anticipated. The 2025 reanalysis was meticulous. Scientists used optical character recognition to convert more than 75,000 pages of Big Ear's archival dot matrix printouts from the 1970s into digital form. These were the original observational records, the unprocessed output of the telescope's receiver. No comprehensive review of this material at this scale had ever been attempted since the signal first appeared. The findings confirmed what Aman had observed that night, but with sharper precision. The WOW signal's flux density surpassed 250 Janskys. At that intensity level, the comet explanation disintegrates entirely. Comets at 1,420 MHz radiate at millijansky levels, thousands of times below the measured value. And the positional reconstruction confirmed what the critics had maintained for years. Neither 266P Christensen nor P/2008Y2 occupied the correct feed horn beam on that date. The geometry was wrong. The output was wrong. The comets could not have generated this signal. So, if the source was not a comet and not a surface-based transmitter and not a satellite, what was it? The leading hypothesis is stranger than any of those options and stranger, in a certain sense, even than extraterrestrial intelligence. Researchers now propose the WOW signal was a rare superradiance event, sometimes described as a hydrogen maser flare, likely initiated by a magnetar. In plain language, under particular and uncommon conditions, a region of cold hydrogen gas can be stimulated into releasing a sudden, intense outburst of radiation at precisely 1,420 MHz. If a magnetar, a neutron star possessing an extraordinarily intense magnetic field, passes near or through such a cloud, it can trigger this kind of coherent emission. The outcome is a one-time cosmic discharge of perfectly tuned energy. Powerful, brief, non-repeating. This mechanism fits every observed characteristic. The frequency is exact because the emission originates from hydrogen itself. The magnitude is consistent with superradiance amplification, which can generate enormous power from a relatively modest cloud. The 72-second duration matches the beam transit time, indicating the source appeared stationary relative to the turning Earth. And the non-repeating nature is explained by the rarity of superradiance events, which require a particular conjunction of conditions that may never realign at the same location. To give the mechanism physical scale, imagine a container of gas that has been slowly compressing under pressure for thousands of years. On a particular day, a spark reaches it. The container does not release pressure gradually. It discharges everything in a single instant. Then it is gone. The conditions that built it no longer exist. You could monitor that patch of sky for another half a century and never observe a recurrence. The WOW signal was not intelligence. It was not comets. It was something the universe generated through natural processes, but so infrequently that nobody had modeled it beforehand. The cosmos created a signal that mimicked everything we expected from an alien civilization at exactly the frequency we were monitoring, and it accomplished this through nothing but physics. This mattered beyond the wow signal itself. It established a template that would recur throughout the story of SETI. Every time researchers believed they had detected technology, the universe produced a natural explanation that no one had anticipated. Pulsars mimicked scheduled transmissions. Comets were implicated and then exonerated. Superradiance manufactured a flawless imitation. And the central question grew harder. If the cosmos keeps generating false positives that are indistinguishable from intelligence, how would we ever recognize the genuine article if it showed up? Return to the Drake equation and examine what happened to every variable that scientists could actually measure. In 1961, the fraction of stars with planets was assumed to be 0.2. Kepler demonstrated it was closer to 1.0. The rate of stellar formation in the Milky Way was placed at 1 per year. Modern surveys put it between 1.5 and 3. The number of potentially habitable planets was thought to be modest. It turned out to exceed 40 billion in our galaxy alone. And then there is abiogenesis, the emergence of life from inert chemistry. Earth coalesced roughly 4.54 billion years ago. The last universal common ancestor of all life on Earth, known as Lua, existed approximately 4.2 billion years ago. The interval is only 300 to 400 million years, and much of that early window was spent while the surface was still molten, still being hammered by infalling rocks, still fundamentally incompatible with biology. Life did not wait for favorable conditions. It appeared almost the instant conditions permitted, possibly sooner. If abiogenesis is routine, and the entire terrestrial record argues that it is, then living systems should be distributed across the galaxy. Every quantifiable variable in the Drake equation has shifted in the optimistic direction since 1961. More stars have planets. More planets occupy habitable zones. Life gets started faster than anyone projected. The galaxy ought to be overflowing. The result of 65 years of listening is 0. That means the filter must occupy one of the variables we have not yet found a way to measure. In 2024, Stern and Guerrier published a paper targeting one specific variable, Fi, the proportion of life-bearing planets that go on to generate intelligence. Drake's initial estimate treated Fi as approaching 100%. If life exists, evolution is persistent. Given enough time, something capable of abstract thought will appear. Intelligence looked like an inevitable terminus. Stern and Guerrier contested this. Their analysis placed Fy between 0.003% and 0.2%, between 3 in 100,000 and 2 in 1,000. Their reasoning was geological. Intelligence at a level that produces technology demands a very particular planetary profile. You need 500 million years or more of active plate tectonics. You need a specific ratio of continental landmass to ocean that allows complex ecosystems to establish themselves on solid ground. You need geological continuity across timescales that most planets simply cannot deliver. To render that probability tangible, fill a jar with 100,000 marbles. Under Stern and Guerrier's lower bound, 3 of those marbles correspond to worlds where life produces intelligence. under their upper bound, 200 do. Compared to Drake's original premise that essentially all 100,000 marbles would qualify, the difference is staggering. If intelligence is genuinely that uncommon, the silence begins to make a different kind of sense. 40 billion habitable planets sounds like a vast pool until you multiply it by 0.003%. That yields approximately 1.2 million worlds with intelligent life across the entire Milky Way, distributed across 13.6 billion years of history. Divide by the galaxy's age, and the number present at any given moment collapses to near nothing. But there is a problem with placing all the explanatory weight on the intelligence bottleneck. Because the very foundation of the rare earth argument, the bedrock on which Stern and Guerrier constructed their case, may not function the way anyone believed. In 2000, Peter Ward and Donald Brownlee at the University of Washington published Rare Earth, a volume that became one of the most persuasive cases for why we might be the only complex life in the universe. Their argument rested on a chain of prerequisites. Complex life demands a stable climate. A stable climate requires plate tectonics to regulate atmospheric carbon dioxide, recirculate nutrients through the biosphere, and help sustain a planetary magnetic field. Plate tectonics, in turn, requires a specific internal heat budget and a mantle of particular composition. Earth possesses all of these. The majority of planets almost certainly do not. The reasoning was elegant. We are unusual because our geology is unusual. For 15 years, Rare Earth served as the standard explanation for our apparent solitude. It integrated smoothly with the Fermi paradox. If tectonic activity is a geological accident, and intelligence requires tectonics, then the great filter is geological. We cleared it. We are on the fortunate side of it. Then the models began contradicting the story. Computer simulations performed between 2015 and 2024 progressively dismantled the neat causal sequence. Some models showed that plate tectonics on Earth may not have preceded the emergence of complex life at all. Instead, tectonics may have developed partly as a consequence of complex life. Biological processes at the surface, particularly the chemical weathering of rock by living organisms, may have weakened the crust sufficiently to allow subduction to initiate. If this is accurate, the relationship runs in reverse. Life does not require tectonics. Tectonics require life. Other models exposed a separate problem. Some simulations demonstrated that plate tectonics can actually retard the oxygenation of an atmosphere, because subduction draws oxidized material back down into the mantle before it can accumulate at the surface. If the very mechanism supposed to enable complex life is in fact delaying it, a load-bearing wall of the rare Earth framework has collapsed. Then there was Pluto. When NASA's New Horizons spacecraft swept past the Pluto system in 2015, it transmitted imagery of geological activity that caught everyone off guard. Pluto's surface showed evidence of icy tectonics, fractured slabs, and what appeared to be convective overturning within a nitrogen ice glacier designated Sputnik Planitia. The feature spans roughly 620 miles across, larger than the state of Texas. Charon, Pluto's principal moon, exhibited comparable structures. These are bodies, billions of miles from any star's warmth, intercepting roughly 1,000th the solar energy that reaches Earth. Active geology there had not been predicted by anyone. The discovery did not establish that plate tectonics are ubiquitous. It demonstrated that geological activity can emerge under conditions far removed from the narrow window rare Earth had described. None of this disproves the notion that intelligence demands specific geology. It complicates it substantially. The once clean narrative, in which a scarce form of tectonic behavior on an unusual world generates an unusual biosphere, keeps getting untidier with each new simulation and each new data point from beyond our solar system. The prerequisites for intelligence may still be demanding, but they may not be the prerequisites we specified. If tectonics are not the scarcity and planets are everywhere and life initiates quickly, the investigation loops back to the underlying problem. Something is removing civilizations from the galaxy before they leave a mark. The available worlds are plentiful. The chemistry is workable. Life launches early. Intelligence may be rare but not inconceivable. Yet across 13.6 billion years and hundreds of billions of stars, the count is zero. In 1996, an economist confronted this exact problem and gave the obstacle a label. Robin Hansen was not an astronomer. He was not a physicist. He was an economist at George Mason University. And in 1996, he released a paper that recast the Fermi paradox in terms a prediction market would recognize. His logic ran as follows. Between inert rock and a galaxy-spanning civilization, there is a long succession of transitions. A planet forming, chemistry producing life, single cells acquiring complexity, intelligence emerging, technology being built, survival long enough to expand beyond a home star. If the galaxy ought to be populated with civilizations but is not, at least one of those transitions must carry a near-zero probability. A choke point so severe that almost nothing makes it through. Hansen named this the Great Filter. The concept is fundamentally probabilistic. You need not know which step is the difficult one. You need only accept that the silence demonstrates a filter exists somewhere in that chain. The arithmetic demands it. If every transition were reasonably probable, the galaxy would be visibly saturated with evidence of intelligence. It is not. Therefore, at least one transition has a pass rate approaching zero. The critical question is not whether the filter exists. The silence settles that. The critical question is where it sits in the sequence. And this is where the concept stops being abstract and becomes personally consequential. If the great filter lies behind us, somewhere among the early transitions, then we already cleared it. Perhaps the origin of life is the hard step, and our planet simply got fortunate. Perhaps the leap from single-celled organisms to complex multicellular life is statistically improbable, and Earth happened to make it. If the filter is behind us, we are uncommon but not threatened. The dangerous part is behind us. If the great filter lies ahead of us, somewhere in the later transitions, then every civilization that reaches our current level of technology eventually collides with a barrier it cannot survive. Nuclear conflict, ecological breakdown, engineered disease, something we have not yet conceived. Under this reading, the silence is a record of deaths. Every civilization that developed as far as we have is gone or going. Hansen stated this as a binary. Behind or ahead, lucky or condemned. And for years, the case for optimism seemed stronger. The emergence of complex life does appear to be genuinely improbable. Earth spent roughly 2 billion years locked at the single-celled stage before multicellularity arrived. Intelligence required another 2 billion years after that. These are immense timescales, and the probability at each transition may be vanishingly small. It seemed reasonable, even probable, that we had already navigated the worst of the gauntlet. To give the stakes concrete shape, imagine 100 civilizations beginning the journey from basic chemistry to interstellar expansion. If the filter is behind us, 99 of them never advance beyond microbial life, and we are the one that did. Unsettling, but finished with the hard part. If the filter is ahead, all 100 develop technology, and 99 are destroyed before any of them can leave their home systems. We have constructed the rockets. We have constructed the radio observatories. We have not yet reached whatever threshold destroys the others. For 2 decades after Hansen's paper, the dispute remained roughly balanced. Credible cases on both sides. No decisive data either way. Then, in 2024 and 2026, 2 papers arrived that shifted the weight decisively toward the worst-case interpretation. Both identified filters that await us. Both described mechanisms already measurable in present-day data. Michael Garrett is an astrophysicist. In 2024, he published a paper contending that artificial intelligence is the great filter. His case was built on a chronology. Earth generated its first radio transmission in 1895, when Guglielmo Marconi sent signals across a distance of roughly 1.25 miles. 127 years later, in 2022, generative artificial intelligence systems began performing at a level that astonished even the people who built them. The interval between first radio wave and sophisticated machine cognition spanned just over a century. Garrett's model holds that any technological civilization traces a similar trajectory because the underlying forces are universal. Once you develop electronics, the drive toward increasingly autonomous computation is not optional. It is propelled by economic competition, military ambition, and the intrinsic logic of making tools more capable. Garrett's estimate for the EC's window between the development of artificial intelligence and the destruction or fundamental transformation of the civilization that built it is approximately 200 years. Not thousands, not millions. 2 centuries. That is the total span during which a civilization might be broadcasting signals while still existing in a form that produces them. Apply that window to the Milky Way. The galaxy is 13.6 billion years old. A civilization's detectable window lasts 200 years. Finding another civilization broadcasting simultaneously would be like trying to photograph a specific lightning strike during a thunderstorm lasting 4 million years. Even if millions of civilizations have existed across the galaxy's history, the odds of any 2 of them overlapping during their respective 200-year windows is negligibly small. The model does not require AI to physically annihilate a civilization. It accounts equally for scenarios in which AI transforms a civilization into something alien to us. Species that merges with its machines or is superseded by them, or simply ceases to broadcast because its AI successor has no use for radio waves. The detectable signature vanishes. The civilization goes dark. Examine Earth's own trajectory. Military radar, the loudest signal our planet generates, operates at roughly 10 to the 14th watts in directed bursts. Those signals are detectable by a Greenbank-class telescope up to about 200 light-years distant. But we are already pivoting toward fiber optic cable, compressed digital transmission, and tightly focused communication that does not leak into space. Earth is growing quieter each year. Within a few decades, our unintentional electromagnetic emissions may fall beneath the detection threshold of any plausible alien observatory. We are closing our own window from within. To put 200 years in physical terms, imagine the full history of the Milky Way as a single mile of road. 200 years is roughly 1/5 of 1 inch. That is the strip of pavement during which any given civilization is broadcasting into the dark. Everything before and after is silence. Garrett's paper was not the only one to propose a filter ahead of us. In February of 2026, a researcher proposed a mechanism that requires no machines at all. Darren J. Dugan put forward a different driver of civilizational collapse. His filter requires no machines turning against their builders. It requires no warfare, no asteroid impacts, no external catastrophe of any kind. It requires only one thing: a species clever enough to separate reproduction from survival, and it is already legible in the demographic data of every industrialized society on Earth. Birth rates are declining across the developed world as a direct consequence of prosperity and individual choice. Dugan's model treats this as a universal property, an unavoidable feature of any species intelligent enough to govern its own fertility. The question his paper poses is whether any civilization can reverse the trend before the mathematics becomes irreversible. The mathematics is already moving. South Korea's total fertility rate in 2024 was 0.72. That means for every 2 adults, there are fewer than 1 child born. Replacement level is 2.1. South Korea is not at half replacement. It is at 1/3. Japan sits at 1.2. Italy at 1.24. China dropped below replacement in 2022 and is accelerating downward. The United States fell below replacement in 2021. These are not forecasts. These are census figures. Dugan's model does not frame fertility decline as a policy problem awaiting a solution. He treats it as a thermodynamic inevitability, in the same category as entropy. His argument proceeds as follows. In any species that evolves general intelligence, individuals eventually acquire the capacity to choose whether or not to reproduce. Once that choice is available, the calculation shifts. Children require enormous investments of time and material resources. In a subsistence society, children are productive labor. In a technological society, children are an expense. Every government that has attempted to reverse the trend has come up short. Pronatalist initiatives in Scandinavia, Japan, Singapore, and Hungary have generated temporary upticks of a few percentage points before decline resumed. France, home to the most generous family support infrastructure in Europe, still dropped below replacement. Dugan's projection extends current global trends forward. Human population peaks around 2080 at roughly 10 billion. Then begins a contraction that gathers speed with every generation. By 2050, his model projects fewer than 100 million humans remaining on Earth. By 3000, functional extinction. A species that once covered a planet, dissolved into empty nurseries. The biological analogy is bacterial. A petri dish colony that depletes its nutrients and collapses. But Dugan's filter is more unsettling than starvation. In the petri dish, the bacteria exhaust their food supply. In his model, the food is still present. The civilization simply stops consuming it. And if this mechanism is universal, if every intelligent species that gains mastery over its own reproduction follows the same downward arc, it explains the silence without requiring any catastrophe at all. No nuclear exchange, no impact event, simply a gradual, quiet dissolution across every inhabited world in every galaxy. Civilizations rise, develop technology, sever sex from reproduction, sever reproduction from survival, and dissolve over the span of a few hundred generations. The galaxy populates itself with ruins rather than colonizers. Two filters, then: Garrett's AI window of 200 years and Dugan's depopulation arc spanning 500 to 1,000 years. They are not mutually exclusive. A civilization might confront both simultaneously, and both papers were published within 2 years of each other, grounded in trends already visible in present human data. For decades, the prevailing view held that the great filter was behind us. The hard transition was the emergence of life, or the jump to multicellular complexity, or the appearance of intelligence. We had already cleared those obstacles. The recent evidence says otherwise. The filter is ahead, and we are presently inside the danger zone. But both of these filters assume that civilizations self-destruct or quietly dissolve. There is another possibility that receives less attention because it does not involve extinction at all. What if civilizations do not end? What if they simply stop being audible? Here is a fact that undermines the fundamental premise of the search for extraterrestrial intelligence. Earth is getting quieter. In the 1960s and 70s, humanity was electromagnetically loud. Omnidirectional radio transmissions, television broadcasts, and military radar installations pumped radiation into space in every direction simultaneously. Military radars, Earth's most powerful emissions, peak at roughly 10 to the 14th watt in their directed beams. A telescope the diameter of Green Bank, 100 meters across, could resolve those signals from about 200 light-years away. That sounds substantial. It is not. 200 light-years encompasses roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. Our loudest transmissions reach 0.00004% of the galaxy, and we are growing quieter each year. Fiber optic cables carry information through glass rather than atmosphere. Cellular networks use low-power nodes aimed downward, not outward. Digital signals are compressed and encrypted, rendering them indistinguishable from random static to a distant receiver. Military radar is migrating toward phased arrays that concentrate energy in precise beams, rather than dispersing it in every direction. Earth in 1970 was a bonfire visible for miles. Earth in 2026 is a flashlight pointing at the floor. Seth Shostak at the SETI Institute has been making this observation for years. Advanced civilizations are not noisier than primitive ones. They are quieter. A civilization 1,000 years ahead of ours might conduct all communication through tightly focused laser pulses, quantum encrypted channels, or technologies we have not yet conceived of. Their transmissions would be undetectable to us because efficiency selects inherently for directed, low-leakage communication. Think of it as the evolution of announcement. A medieval town crier shouts news in the public square. Everyone within earshot receives it. A contemporary postal system delivers correspondence to individual addresses. The volume of information conveyed has grown by orders of magnitude, but the noise has fallen to nothing. A civilization employing tight beam communication could be exchanging more information in a single second than humanity has broadcast across its entire radio-emitting history. And we would be completely unaware of it. An alien civilization observing Earth. from 500 light-years distant in 1970 would have captured our television transmissions. The same civilization observing Earth in 2070 might detect nothing at all. We would appear to have vanished, and this logic runs in both directions. A civilization 500 light-years away that underwent the same technological transition 500 years ago would already be invisible to us. We could aim every telescope we possess at their star and hear only silence because they had already upgraded their infrastructure. The entire rationale of SETI, listening for electromagnetic leakage, depends on catching civilizations during a narrow phase when they are advanced enough to generate detectable transmissions, but not yet efficient enough to contain them. That phase might last a century, perhaps two. On a cosmic timeline of 13.6 billion years, 200 years registers as nothing. It is a camera shutter. Two civilizations would both need to occupy their leaky phase simultaneously, positioned within detection, range, and pointed at one another. The probability of that coincidence diminishes with each decade that any civilization becomes more efficient. Perhaps the silence, then, is the signature of graduation. But certain researchers were not content with monitoring for leakage. They wanted to search for something grander, something with a physical footprint visible across the full extent of the galaxy. In 2024, a project called Hephaistos published findings that generated international attention. The team had surveyed approximately 5 million stars within 300 parsecs, roughly 1,000 light-years, hunting for something no one had ever sought at that scale. Dyson spheres. The concept originates with physicist Freeman Dyson in 1960. A sufficiently advanced civilization, he argued, would eventually exhaust the energy supply available from a single planet. The logical progression would be to erect a structure surrounding its host star, a shell or distributed swarm of collectors intercepting the star's complete energy output. Such a structure could not be invisible. The laws of thermodynamics make this certain. It would absorb the star's visible light and irradiate that energy as infrared heat. No matter how refined the engineering, waste heat is inescapable. From a distance, a star enclosed by a Dyson sphere would appear dimmer in visible wavelengths and brighter in mid-infrared. That is precisely what Hephaistos found. 7 M-dwarf stars displayed anomalous mid-infrared excess that resisted explanation by any known astrophysical mechanism. M-dwarfs are small, cool, long-lived stars, the most numerous stellar type in the galaxy. They are also the most energy-efficient candidates for a megastructure project because they burn for trillions of years, vastly longer than stars of our type. A civilization building for permanence would select an M-dwarf for the same reason you build a home on solid ground rather than a floodplain. All 7 candidates passed multiple screening, filters. The infrared excess was genuine. It was measured. It was consistent with what a partial Dyson sphere, one that does not fully enclose its host star, would produce. The paper was careful to enumerate natural explanations, such as circumstellar dust or debris disks, but noted that none of them satisfactorily reproduced the observed spectral shape. The infrared profile did not match any standard model of dust around a cool star. Something anomalous was occurring around those 7 worlds. The reaction was immediate. Media outlets published headlines about potential alien megastructures. Social media lit up. The paper accumulated hundreds of thousands of views within days. For a brief interval, the scientific community permitted itself to seriously entertain the possibility that someone, somewhere, had engineered something around a star. To appreciate the scale of what a Dyson sphere would represent, Earth intercepts roughly 1/1000th of our star's total energy output. A complete Dyson sphere would capture all of it. A billion-fold increase in accessible energy. A civilization commanding that much power could accomplish things we cannot currently formulate. Operate interstellar transmitters detectable across the entire galaxy. Run computational systems the mass of planets. Physically restructure their solar system. For comparison, the combined output of every power plant humanity has ever built is roughly 10 to the 13th watts. A Dyson sphere surrounding a star like ours would yield roughly 3.8 times 10 to the 26th watts. The gap between human civilization and a Dyson sphere civilization spans 13 orders of magnitude. That is why the Hephaistos result mattered. It was a physical measurement of real infrared light from real stars behaving in ways that were difficult to account for. The team was cautious. They did not assert they had discovered aliens. They asserted they had discovered anomalies deserving investigation. Within months, however, those anomalies would receive a very different interpretation, and it was one that no one involved in the original survey had considered. The follow-up analysis came in 2025. Independent research groups re-examined the 7 M-dwarf candidates using supplementary infrared and optical data. What they found was not alien megastructures. It was background contamination. The anomalous infrared excess was real. It simply was not originating from the stars themselves. It was coming from objects behind them, billions of light years more distant. Dust-obscured galaxies catalogued in the literature, and active galactic nuclei, the supermassive black holes at the cores of remote galaxies that pour out enormous energy as they consume surrounding matter. These background sources happen to lie along the same lines of sight as the M-dwarf targets. Their infrared emissions blended with the stellar flux, generating the appearance that the stars were producing excess heat from their own vicinity. The angular resolution of the original survey was not sufficient to disentangle foreground stars from background galaxies at those scales. Once higher resolution data was applied, separating the faint glow of distant galaxies from the light of nearby stars, the megastructure signatures dissolved. The stars were unremarkable. The infrared excess belonged to objects with no connection to them. The universe had done it again. It had reproduced the exact signature of advanced technology using nothing more than random cosmic geometry and hot intergalactic dust. This had not been the first occasion. In 1967, Jocelyn Bell Burnell recorded a signal so metronome regular that her team designated it LGM-1, Little Green Men. It was a pulsar, a rotating neutron star sweeping a beam of energy across space. In 1977, the WOW signal satisfied every criterion for an artificial extraterrestrial transmission. Decades of subsequent analysis point toward a natural origin. Likely a magnetar-triggered hydrogen, maser flare from interstellar gas along the line of sight. In 2020, BLC-1 presented every appearance of a signal from Proxima Centauri. It was electronic interference generated near the Parkes telescope. Now, in 2024, 7 stars bore every hallmark of partial Dyson spheres. They were background galaxies. The pattern is coherent, and it is unsettling. Every time we believe we have found something, nature provides a natural explanation that nobody had predicted in advance. The universe is systematically deceptive. It generates phenomena that appear engineered, that pass our filters, that survive initial scrutiny and then resolve into ordinary physics under closer examination. A Dyson sphere search spanning 5 million stars, the most ambitious ever undertaken, reduced to zero by geometry and dust. 5 million stars and not a single megastructure, not one hint of deliberate construction at any scale. The physical analog is a highway mirage. On a hot day, the road surface ahead seems covered in water. The light is real. The refraction is real. The physics generating the illusion is fully genuine. But the water does not exist. You can drive toward it indefinitely and never arrive. The Hephaistos result was a cosmic mirage. 7 candidates, all accounted for by geometry and distance. And it raises a question that underlies all of CETI. If the universe keeps generating false positives that confound our most sophisticated instruments, how much confidence can we have in our ability to recognize an authentic signal if one ever appeared in our data? The answer is increasingly not much. But false positives and cosmic mirages represent one category of explanation for the silence. There's a darker one. What if the civilizations are genuinely out there, real and present, and they are actively concealing themselves? In 2008, Chinese science fiction author Liu Cixin published the second volume of his 3-body trilogy. It was called The Dark Forest. The novel proposed a resolution to the Fermi paradox that was structurally elegant and morally chilling. It worked like this. The universe is densely populated with civilizations. All of them are silent because disclosing your location is functionally equivalent to requesting your own destruction. The reasoning follows from 2 axioms. First, survival is the paramount drive of every civilization. Second, civilizations expand and consume resources continuously. But the total matter and energy available in the universe is finite. These 2 premises generate an inescapable conflict. Resources are bounded. Appetites are not. Any civilization that encounters another must decide, cooperate or eliminate. But cooperation demands trust. Trust requires communication. Communication reveals your position. Here is where game theory becomes lethal. You cannot verify another civilization's intentions. They might be peaceful today and predatory in a millennium. They might be technically inferior now and superior within a century. The only guarantee of safety is to eliminate the other civilization before it becomes capable of threatening you. And because every surviving civilization has recognized this same logic, every civilization that still exists has already learned the same lesson. Remain silent. Remain hidden. Destroy anything that announces itself. Liu Cixin called this the Dark Forest. Imagine a forest at midnight filled with armed hunters. Every hunter knows the forest harbors other hunters. No one can see more than a few feet ahead. Every sound, every movement might draw fire. The rational strategy is absolute stillness and an immediate response to any noise. The cosmos, in this model, is dense with armed civilizations standing motionless in the dark. The hypothesis carries a specific physical implication. A dark forest civilization would not construct Dyson spheres because Dyson spheres are detectable across galactic distances. It would not broadcast radio waves because radio waves disclose position. It would not expand aggressively because expansion leaves a visible trail. It would minimize its detectable signature in every way available. From the outside, it would appear exactly as silent as the silence we observe. The concept was not entirely original. John Ball had proposed the zoo hypothesis in 1973. suggesting advanced civilizations might deliberately withhold contact from primitive species, the way a nature preserve separates human visitors from the animals within it. The dark forest extends this idea significantly. They are not merely avoiding contact. They are avoiding existence as a detectable phenomenon, because detection is an existential risk. Critics of the dark forest hypothesis identify several vulnerabilities. It presupposes a level of universal paranoia that may not apply to every civilization. It requires that every civilization independently arrives at identical conclusions with no exceptions, because a single openly broadcasting civilization would rupture the silence. It also assumes that neutralizing a distant civilization is easier than communicating with it, which is not obviously true given the distances separating star systems. But the hypothesis possesses one quality that resists dismissal entirely. It is consistent with all available data. The silence we observe is exactly what a dark forest universe would produce, and it connects directly to a real and ongoing controversy on Earth, one that has divided the scientific community around the question of whether we should be deliberately shouting into that forest. In 1999, a Russian astronomer named Alexander Zaitsev did something that no international authority had sanctioned and no scientific consensus had endorsed. He used the Evpatoria planetary radar installation in Crimea, a dish constructed originally for deep space communication with Soviet spacecraft, to beam a high-powered, precisely targeted message toward several nearby star systems. He called it Cosmic Call. The Soyuz transmission was engineered to be detectable by any civilization possessing a radio telescope comparable to our own. It encoded mathematical and scientific information in a format intended to be interpretable by any technologically capable species. Zaitsev did not consult the SETI community before transmitting. He did not request authorization from any government. He did not seek international review. He was not required to do any of these things because no binding international protocol governs deliberate transmissions into space. None exists. Guidelines exist. The International Academy of Astronautics has issued a set of recommendations, but they carry no enforcement mechanism. No treaty, no statute, no enforceable agreement prevents anyone possessing a sufficiently powerful transmitter from broadcasting humanity's existence and location into the cosmos at any moment. Today, this hour. The response within the scientific community was swift and contentious. David Brin, the physicist and novelist who had written at length about the Fermi paradox, characterized it as reckless and potentially ruinous. If the dark forest hypothesis were correct even with low probability, Brin argued, deliberately transmitting was equivalent to igniting a signal fire in a wilderness full of predators. Brin resigned from SETI-affiliated committees in protest over what he described as the complete absence of governance around active messaging, a practice the community refers to as METI. Messaging to Extraterrestrial Intelligence. Jill Tarter, who had spent 35 years directing SETI searches including Project Phoenix, and who served as the real-world inspiration for the protagonist of the film Contact, found herself positioned uncomfortably between the factions. She supported the search but harbored reservations about transmission. Dan Wertheimer, a Berkeley astronomer, argued that any deliberate transmission ought to require global consensus. The prospect of one person or one nation making a choice that could determine the fate of the entire species struck him as unacceptable. Seth Shostak at the SETI Institute held the opposing position. His reasoning was pragmatic. Earth's military radar systems have been leaking detectable signals into space for decades. Any civilization within 200 light-years possessing technology sufficient to pose a threat to us already knows we exist. Deliberate transmission alters nothing. Concealment is futile because we were never concealed. Consider it from this angle. You are standing in a darkened room, and you have been coughing audibly for 70 years. Someone proposes that perhaps you should stop coughing. But you have been coughing the entire time. If something in that darkness intended to locate you, it already has. The dispute has never been resolved. It cannot be, because the underlying question is unanswerable with current knowledge. Is the universe dangerous, or is it not? And the schism reveals something that most people believe about science, but which is incorrect. People assume the scientific community manages humanity's relationship with the cosmos in an organized way, that protocols exist and oversight is in place and institutional control governs what humanity broadcasts toward the stars. It does not. The METI controversy demonstrated that any individual with access to adequate equipment can speak on behalf of our entire species. And, regardless of whether anyone out there is receiving those transmissions, the instruments we have constructed to find answers keep disappearing. On December 1st, 2020, the 900-ton receiver platform of the Arecibo Observatory broke free of its support cables and fell through the 305-meter radio dish below. The collapse was not sudden. Engineers had been alerting authorities to cable deterioration for months. 2 cables had already snapped in August and November. The National Science Foundation decided not to attempt repairs because deploying workers onto the compromised structure was too dangerous. When the platform fell, it shattered the dish, the instrument that had been the world's largest single-aperture radio telescope for 53 years. The NSF chose not to rebuild it. Arecibo had contributed to SETI at Home, Project Phoenix, radar mapping of near-Earth asteroids, pulsar research, and atmospheric science. It was among the most productive scientific instruments ever constructed, and it was gone. But Arecibo was not the first to disappear. The Big Ear Telescope in Ohio, the instrument that recorded the WOW signal in 1977, was raised between 1997 and 1998, so the land could be converted to a golf course. The strongest candidate signal in the entire history of SETI, and the telescope responsible for capturing it, were paved over for a driving range. The Allen Telescope Array, a field of 42 dishes in Northern California, designed expressly for SETI, was developed as a joint undertaking of the SETI Institute and the University of California at Berkeley. Each dish measures 6 meters in diameter and operates across 1 to 14 gigahertz. In 2011, the array entered hibernation. The cause was financial. The SETI Institute could not sustain $1.5 million per year of operating costs. For reference, a single F-35 fighter aircraft costs $80 million. The array was subsequently reactivated through private donations, but the hibernation period illustrated a persistent pattern. Then there is the federal funding record. NASA's first dedicated SETI program, the High-Resolution Microwave Survey, launched in 1992 with an annual budget of $12 million. It combined a targeted component using Arecibo with an all-sky survey conducted at the Goldstone Deep Space Network antenna. Senator William Proxmire had already terminated an earlier NASA SETI initiative in 1981 by awarding it his Golden Fleece Award, a distinction he had invented for government spending he considered wasteful. Carl Sagan, personally lobbied Proxmire and persuaded him to reverse course. But in 1993, Senator Richard Bryan of Nevada eliminated the program permanently. It had been operational for 1 year, $12 million. That is roughly the cost of 600 feet of interstate highway construction. Since 1993, every significant SETI undertaking has depended entirely on private money. The search for an answer to one of the most fundamental questions our species has ever formulated, are we alone in the universe, depends entirely on the generosity of private donors and the occasional billionaire willing to fund it. The pattern is difficult to ignore. The telescope that produced the best signal was demolished for real estate. The telescope array designed for the search was mothballed over pocket change. The federal program was canceled for political reasons, and the largest radio dish in the Western Hemisphere was allowed to collapse and was never rebuilt. If you were designing a civilization with the explicit goal of never detecting an extraterrestrial signal, this is roughly the approach you would take. In 2015, a Russian-Israeli billionaire named Yuri Milner took the stage in London alongside Stephen Hawking and announced Breakthrough Listen, $100 million over 10 years, dedicated to the most comprehensive search for extraterrestrial intelligence ever mounted. It represented the largest single funding injection in the history of SETI. Milner simultaneously announced Breakthrough Starshot, a separate $100 million commitment toward developing technology to propel gram-scale probes to the nearest star systems at 20% of the speed of light. Breakthrough. Listen secured access to several of the most powerful radio telescopes on Earth. Green Bank in West Virginia, 100 meters in diameter, the world's largest fully steerable radio dish. Parkes in Australia, 64 meters, one of the Southern Hemisphere's most sensitive radio instruments. Meerkat in South Africa, a formation of 64 dishes engineered for the next era of radio astronomy. And the Automated Planet Finder at Lick Observatory in California, a 2.4-meter optical telescope capable of detecting laser pulses sent from distant worlds. The strategy was straightforward in outline. Aim the finest instruments at the most promising candidates and listen across every frequency band simultaneously. By 2024, the project had examined approximately 1 million nearby stars and accumulated more than 2 petabytes of data, a volume that would occupy roughly 400,000 DVDs. Its sensitivity was extraordinary. Breakthrough Listen could detect a transmitter generating 10 to the 12th through 10 to the 13th watts, roughly equivalent to the total output of a small nuclear power plant from nearby star systems. Any civilization within a few hundred light years broadcasting at those power levels would register in the data. To calibrate that sensitivity, Breakthrough Listen could detect the equivalent of a single large television transmitter from a planet orbiting within the nearest 1,000 stars. If any civilization in the neighborhood was making any deliberate effort to be heard, these instruments would have found it. None did. 2 petabytes of silence. 1 million stars examined. Thousands of hours of observation across 4 major instruments on 3 continents. The result was identical to the result SETI had been getting since Frank Drake pointed an 85-foot dish at 2 stars in 1960. 0. Then, in 2020, one of Breakthrough Listen's own instruments captured something that caused the entire team to hold its breath. Parkes, the 64-meter dish in New South Wales, registered a narrowband signal at 982.002 MHz. Narrowband signals carry significance because natural astrophysical sources almost invariably produce broadband emissions, energy distributed across a wide range of frequencies. A narrowband signal concentrated at a single frequency is one of the defining hallmarks of an engineered transmission. And this one appeared to originate from the direction of Proxima Centauri, the nearest star to our Sun, 4.24 light-years distant, a star already established to host at least 2 planets, one sitting within the habitable zone. The signal was designated BLC-1, Breakthrough Listen Candidate 1. It was the first signal the project had ever judged promising enough to earn a formal candidate classification. For the researchers involved, the months that followed ranked among the most intense in the modern history of SETI. BLC-1 drifted in frequency. This was significant. When a signal originates from a source on a rotating planet, that rotation produces a Doppler shift, a gradual change in the received frequency over time. Earth surface interference typically does not drift in the same pattern because the transmitter and receiver share the same rotating body. BLC-1's drift rate matched what you would predict from a transmitter on a planet orbiting Proxima Centauri. The signal appeared exclusively when the telescope was aimed at Proxima Centauri. When the dish moved to observe a reference direction away from the star, the signal vanished. When the dish swung back toward Proxima, the signal returned. This on-off test is the standard procedure for distinguishing celestial sources from local interference. BLC-1 passed it. For months, the Breakthrough Listen team worked in near isolation. They reprocessed the data multiple ways. They audited all known interference sources. They cross-checked against catalogs of terrestrial transmitters, satellites, overflying aircraft, and ground-based electronics. They applied every filter in their analytical pipeline. BLC-1 survived them all. Word eventually reached the press in late 2020. The story appeared in outlets worldwide. Scientists who had spent decades calibrating public expectations about SETI found themselves confronting a question they had always hoped to answer, but never anticipated facing so directly. Was this it? It was not. In 2021, the Breakthrough Listen team published a thorough analysis demonstrating that BLC-1 was almost certainly human-generated radio frequency interference. The decisive evidence was the identification of structurally identical signals at adjacent frequencies, signals sharing every characteristic of BLC-1, but originating from directions with no relationship to Proxima Centauri. The most probable source was electronics operating in the immediate vicinity of the Parkes telescope itself. Intermodulation products, spurious signals generated when multiple radio frequency sources interact and produce emissions at new frequencies. The drift rate that had seemed so compelling fell within the range that local interference can produce under particular conditions. It was not unique to a planetary source. The on-off behavior could be accounted for by the telescope's side lobe response, secondary sensitivity regions outside the primary beam, which intermittently captured local signals depending on pointing direction. BLC-1 was electromagnetic noise from approximately 0 light-years away. The most promising SETI candidate in decades had been manufactured by human technology sitting within the telescope's own compound. Imagine hearing a knock at your door in the middle of the night. You look through the peephole. No one. You open the door. No one. You step outside and hear the knock again, and then realize it has been emanating from pipes inside your own wall. BLC1 was the knock in the pipes. The disappointment ran deeper than disappointment. It was methodological. BLC1 demonstrated that even the most sophisticated SETI pipeline in existence, backed by $100 million in funding and decades of accumulated expertise, could be fooled by a signal originating a few hundred feet from the antenna. If local interference can reproduce every attribute of an extraterrestrial transmission, the threshold for a confirmed detection is effectively unreachable using a single instrument. Any credible claim would require simultaneous confirmation from multiple independent telescopes on separate continents, each recording the same signal at the same moment and independently eliminating every possible terrestrial explanation. BLC. One joined the WOW signal and the Dyson sphere candidates on an expanding list of phenomena that almost were, but were not. And while Breakthrough Listen was chasing a ghost from next door, a new generation of instruments had launched the largest systematic survey ever attempted. The findings were already in, and they were unchanged. In March of 2023, an instrument called COSMIC came online at the Very Large Array in New Mexico. The VLA is an icon of radio astronomy. 27 dishes deployed across the desert in a Y-shaped arrangement, each dish 25 meters across. COSMIC, which stands for Commensal Open Source Multi-Mode Interferometer Cluster, does something no previous SETI instrument had accomplished at this scale. It piggybacks on routine astronomical observations. Whatever the VLA is examining on any given night, COSMIC processes the identical data stream in parallel, scanning for narrowband signals that might indicate a technological source. COSMIC acquires telescope time at no cost. It does not displace other scientific programs. It simply monitors everything the VLA monitors and conducts its own analysis concurrently. In its first 11 months of operation, COSMIC observed more than 950,000 distinct sky fields encompassing 267,510 individual stars. It scanned across 2 to 4 gigahertz, a frequency range that includes the water hole, the quiet corridor between the hydrogen line at 1,420 megahertz and the hydroxyl line at 1,665 megahertz, long regarded as the most logical frequency range for a deliberate interstellar signal. The result from those 11 months: 0 technosignatures. COSMIC was not the only large-scale search in operation. In 2024, the Murchison Wide Field Array in Western Australia, a low-frequency radio telescope array, surveyed 2,800 entire galaxies for technosignatures. Not individual stars. Galaxies, each containing hundreds of billions of stars. The premise was that a sufficiently advanced civilization, one that had achieved engineering at galactic scale, might generate signals detectable across intergalactic distances. The MWA found nothing. In October of 2024, the Allen Telescope Array conducted the longest sustained SETI observation ever directed at a single target. 28 hours pointed at TRAPPIST-1, a red dwarf star 39 light-years away, hosting 7 rocky planets, 3 sitting within the habitable zone. The observation generated 2,264 candidate signals. Every single one was traced to terrestrial origin. Then, in July of 2025, an object arrived in the solar system from interstellar space. 3. I/Atlas. The third confirmed interstellar visitor ever detected, following Oumuamua in the 2017 and Borisov in 2019. The ATA was aimed at it within days. Over 7.25 hours of observation, the array recorded 74 million narrowband hits. Automated filters reduced that to 211 candidates meriting closer scrutiny. The final tally: 0. 74 million signals arriving from the direction of an object that originated in another stellar system. Not one was artificial. The surveys exceed by orders of magnitude anything Frank Drake could have envisioned when he pointed his 85-foot dish at 2 stars in 1960. The instruments are more sensitive. The frequency coverage is wider. The analysis accelerates each year as artificial intelligence now processes breakthrough listen. Data 600 times faster than conventional methods. And the answer has not changed. It was 0 in 1960. It was 0 after 1 million breakthrough listen stars. It was 0 after 950,000 cosmic sky fields and 74 million narrowband hits from an interstellar visitor. At some threshold, the absence of evidence begins to constitute evidence of absence, and that forces a question this investigation can no longer sidestep. For decades, a standard defense against the silence existed. Jill Tarter, who spent 35 years directing the search for extraterrestrial intelligence, articulated it this way. Imagine you want to know whether the ocean contains fish. You walk to the shore, scoop up a single hot tub's worth of water, examine it, and find nothing. Would you conclude the ocean is empty? That was the argument. All of SETI's searching, every dish aimed at every star, every frequency scanned, every algorithm executed, amounted to a hot tub scooped from a cosmic ocean. Less than 1% of the sky has been examined at the frequencies and sensitivities that matter. Earth's radio bubble, the expanding sphere of electromagnetic emissions leaking outward from our planet, encompasses roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. We are undetectable to 99.9999% of the galaxy. The hot tub argument sounded reasonable. It projected appropriate humility. For a long time, it was sufficient to keep the question open, without demanding uncomfortable answers. But it has stopped working. The problem is accumulated data. SETI at home ran for 21 years. Volunteer computers processed 12 billion candidate signals. Breakthrough Listen scanned approximately 1 million nearby stars and gathered more than 2 petabytes of raw observations. The cosmic search on the Very Large Array covered 950,000 sky fields in under a year. The Murchison Wide Field Array surveyed 2,800 entire galaxies. The Allen Telescope Array observed TRAPPIST-1 for 28 continuous hours during planetary transits, producing 2,264 candidate signals that all turned out to be terrestrial. Each of these programs employed different instruments, different frequency ranges, different analytical methods, different sections of the sky. The combined result was always the same figure. Statistical models based on 6 decades of null results now estimate fewer than 1 to 5 detectable technosignatures per century across the entire Milky Way. That is no longer a hot tub. That is a measurement. The ocean has been sampled at enough locations with enough variation across enough time that the absence of fish is beginning to tell us something true about the nature of the ocean itself. The shift is understated, but it transforms the investigation. For 60 years, the silence was treated as a gap in knowledge, an empty space waiting to be filled by more capable instruments or more patience. The emerging interpretation treats the silence as data in its own right, the same way a blood test returning a negative result is still a clinical finding. Zero is not nothing. Zero is a result. And that result settles on the investigation like a physical weight, because it closes the most comfortable exit available. You can no longer say we simply have not searched hard enough. Not after 12 billion processed candidates and 74 million narrowband hits from an interstellar visitor, all resolving to the same figure. The hot tub defense sustained researchers for decades. It granted permission to keep searching without confronting what the silence might signify. Now it is eroding under the sheer accumulated mass of nothing. And if the silence constitutes genuine data, then the question shifts its shape entirely. It stops being about why we have found nothing yet, and becomes a question about what zero actually means. That is a qualitatively different inquiry. And it begins with the instruments we believed we could rely on to detect life in the first place. There is a molecule that biologists have depended on for decades as a marker for life. Oxygen. Free molecular oxygen, the variety that sustains your breathing, is chemically aggressive. It bonds with iron, carbon, silicon, and dozens of other elements with readiness. Leave a planet to its own processes for a few million years without something continuously regenerating the oxygen supply, and it disappears from the atmosphere entirely. On Earth, that replenishing mechanism is photosynthesis. Plants and cyanobacteria split water molecules using solar radiation, discharge oxygen as a byproduct, and maintain the atmosphere at roughly 21% concentration. The logic seemed airtight. If you examine the atmosphere of a distant world and detect free oxygen, something biological is almost certainly sustaining it, because nothing else is capable of doing so. Oxygen became the premier biosignature, the single most reliable indicator that a planet might sustain life. The James Webb Space Telescope was designed in part to execute exactly this analysis, to study light filtering through exoplanet atmospheres and search for the chemical fingerprints of gases that could not persist without biological processes generating them. Entire research careers were constructed around this premise. Entire missions were authorized because of it. Then, in 2024, a research team discovered oxygen being produced on the floor of the Pacific Ocean without the involvement of any organism. The source was polymetallic nodules, mineral formations sitting on the deep ocean seafloor at depths where no sunlight penetrates, and photosynthesis is physically impossible. These nodules are composed of manganese, nickel, cobalt, copper, and other metals that generate modest but measurable electrical potentials through natural electrochemical processes. The potential is sufficient to cleave seawater into hydrogen and oxygen through electrolysis. No biology required. The researchers measured oxygen production rates that in certain regions of the abyssal plain exceeded the rate at which local microbial communities consumed it. The deep sea floor was generating oxygen faster than the life around it could use it. To put this in perspective, imagine discovering that the smoke detector you have relied on throughout your professional career also triggers randomly when nothing is cooking and nothing is burning. The device still operates, but you can no longer trust the alarm to mean what you always assumed it meant. If oxygen can arise without life on Earth, in Earth's own ocean, it can arise without life on a rocky world orbiting a red dwarf star 40 light-years away. One of the most foundational premises in astrobiology, the equation of atmospheric oxygen with biological activity, had developed a fracture running through its foundation. This did not render oxygen useless as a biosignature. It meant oxygen alone was no longer adequate evidence. You would need corroborating signals, additional gases, other chemical combinations, an entire network of atmospheric fingerprints pointing collectively toward biology rather than toward geology or abiotic chemistry. The difficulty is that James Webb was already struggling to obtain even single-molecule biosignature detections from exoplanet atmospheres. Requiring multiple independent confirming signals from a single planetary atmosphere made an already demanding measurement harder by an order of magnitude. The telescope would need extended observation campaigns, more transit events, and more sophisticated noise characterization for each target. And the one world where the telescope believed it had found a second biosignature, something beyond oxygen, something that on Earth is generated almost exclusively by living organisms, turned out to illustrate precisely how fragile the entire detection framework had become. The planet is K218b. It orbits a red dwarf star 124 light-years from Earth. It is a sub-Neptune, larger than our world but smaller than Neptune, roughly 8.5 times Earth's mass. In 2023, the James Webb Space Telescope analyzed starlight passing through its atmosphere and detected what appeared to be dimethyl sulfide. On Earth, dimethyl sulfide is manufactured almost exclusively by marine phytoplankton, the microscopic organisms drifting through the upper ocean. It is the compound responsible for the characteristic scent of the sea. Finding it on another world would have been remarkable because no known geological or purely chemical mechanism produces dimethyl sulfide in meaningful quantities without biology. The headlines were global and instantaneous. Major news organizations reported the detection as potential evidence of biological activity on an alien world. For a brief interval, K218b became the most discussed exoplanet in both the scientific community and popular media. Then, independent research teams examined the data more carefully. The dimethyl sulfide signal resided within the noise floor of the observation. The statistical confidence of the detection dropped below the threshold. Most scientists consider necessary for a formal discovery claim. Follow-up analyses employing different atmospheric modeling approaches could not consistently reproduce the result. By early 2026, scientific consensus had shifted. The signal was most probably an artifact of the data reduction process, a statistical ghost rather than a genuine molecule in that sky. As of this investigation, no exoplanet possesses a confirmed atmospheric biosignature. Not K218b. Not any of the 7 worlds orbiting TRAPPIST-1. Not the 756 planets confirmed by the Transiting Exoplanet Survey satellite. Not the 2,783 worlds catalogued by Kepler. The most promising next candidate for atmospheric characterization is Gliese 12b, a rocky world 9/10 the radius of Earth in a temperate orbit around its host star, just 40 light-years from us. It is close enough and small enough that James Webb could plausibly analyze its atmosphere across multiple observing campaigns, accumulating signal over dozens of transits to push detection confidence above the noise. Early characterization observations are already scheduled. But after dark oxygen compromised one biosignature, and after K2-18b demonstrated how a statistical artifact can briefly resemble the discovery of living worlds, the goalposts have shifted significantly. The question is no longer simply whether we will find the right planet. The question is whether we would recognize a genuine biosignature if it appeared in our data. A compound that signals life on Earth might signal nothing more than chemistry on another world. A detection that appears clean under one statistical treatment might evaporate under a different approach. The instruments are not broken. The confidence we extended to them was premature. And there exists a hypothesis, one that most active researchers decline to consider seriously, but that none can formally falsify, which suggests the difficulty runs even deeper than imperfect tools. It proposes that we may not be perceiving the actual universe at all. In 2001, science fiction author Stephen Baxter published a thought experiment that most astronomers dismissed at first encounter and none could actually disprove. He called it the planetarium hypothesis. The premise is structurally simple and implicationally disturbing. If a civilization existed that was sufficiently advanced, thousands or millions of years beyond our present technological capabilities, it could encase our solar system within a projected simulation. A perfect replica of an empty universe, projected inward from some boundary, such that every telescope, every space probe, every instrument humanity ever constructs shows us precisely what the builders intend for us to observe. We would perceive an empty cosmos because the cosmos we are permitted to perceive is an engineered display. It sounds like science fiction because it was conceived by a science fiction writer. Baxter was a novelist, not a physicist or an astronomer. But the hypothesis is the logical terminus of an older idea proposed by physicist John Ball in 1973. Ball called his version the zoo hypothesis. His argument was more restrained. Advanced civilizations might deliberately avoid contact with developing species the same way a wildlife sanctuary keeps human observers from interacting with the animals they study. The animals in the sanctuary do not know they are being watched. They do not know the perimeter of the sanctuary exists. They simply inhabit what appears to them to be a natural environment, unaware that their natural environment has been maintained and curated. The planetarium hypothesis carries Ball's reasoning one step further. The advanced civilization does not merely withhold contact from us. It actively constructs the reality we observe. The enclosure is not around us. Everything we see is the enclosure. Scientifically, the hypothesis suffers from a fundamental defect that prevents it from being treated as a legitimate research question. It is unfalsifiable. No observation you could make, no experiment you could design, no data you could collect could demonstrate that you exist inside a planetarium, because any evidence of the simulation could itself be a constructed element of it. That makes it disqualified science by any standard epistemological criterion. It lies entirely beyond the boundary of the scientific method. But it is also fully consistent with everything we observe. Nothing in the laws of physics prohibits a sufficiently advanced civilization from constructing such a projection. The energy requirements would be enormous, roughly equivalent to capturing the complete output of a star, which is precisely what a Dyson sphere is designed to do. And the Dyson spheres we believed we had found turned out to be background galaxies. Whether or not the planetarium hypothesis describes reality is not the point. What it exposes is something disquieting about this entire investigation. Every explanation for the silence, the great filter, the dark forest, the zoo hypothesis, the temporal coincidence argument, each rests on the assumption that we are perceiving the actual universe as it genuinely exists. If that assumption is incorrect, every conclusion built upon it falls away entirely. The hypotheses are accumulating. filters that annihilate civilizations before they spread, forests where civilizations conceal themselves from each other, zoos where advanced species observe primitives, planetariums where observable reality is manufactured. Each answer generates new questions, and none of them can be tested with instruments we currently possess. But there is one piece of hard evidence that cuts through all of this theorizing, because it is not a hypothesis or a thought experiment. It is a measurement extracted from our own planet's geological archive, and it makes everything else harder to explain. Life materialized on this planet almost immediately upon the planet's formation. Earth coalesced approximately 4.54 billion years ago from the gravitational accretion of dust and gas orbiting a young star. For the first several hundred million years, the surface consisted largely of molten rock. Asteroids struck it continuously during the period geologists call the Late Heavy Bombardment. Surface temperatures exceeded anything compatible with the complex chemistry of living systems. By any reasonable standard, conditions were catastrophic for the emergence of biology. Yet the last universal common ancestor, abbreviated LUCA, the single ancestral organism from which every living thing on Earth descends, bacteria, trees, fish, humans alike, existed approximately 4.2 billion years ago. The gap between Earth's formation and the confirmed presence of life is somewhere between 300 and 400 million years. And much of that interval was spent under conditions where life, as we understand it, could not have existed at the surface. Life did not wait for hospitable conditions. It appeared essentially as soon as conditions permitted, possibly even before. To grasp how rapid this is in geological terms, compress the entire 4.54 billion year history of Earth into one calendar year. The planet forms on January 1st. Life appears before the end of February. Dinosaurs do not arrive until December. Humans appear in the final minutes of December, 31st February. That is the interval within which non-living chemistry transitioned to self-replicating biology on this planet. If abiogenesis, the technical term for the process by which inert matter becomes living matter, is this facile and this robust, then it ought to be occurring on rocky planets throughout the galaxy at this moment, and has been occurring for billions of years preceding now. The 40 billion Earth-sized worlds estimated to occupy habitable zones around Milky Way. Stars are potential arenas where the same chemical experiment has been running in parallel across geological time. And yet intelligence required an additional 4.5 billion years to emerge on Earth after life appeared. Detectable technology, the variety that generates radio signals or infrared waste heat, appeared only within the last century. The bottleneck is clearly not the origin of life itself. Single-celled organisms, bacteria and archaea and their analogues, are probably scattered across the galaxy in quantities that make them as ordinary as mineral grains. The bottleneck may not even be intelligence, though Stern and Garrier's estimate of 0.003 to 0.2% of life-bearing planets generating intelligent species makes that transition formidably improbable. Earth itself spent more than 3 billion years exclusively populated by single-celled organisms before multicellular life appeared. That is not a minor pause. That is most of the planet's entire history. The real bottleneck may reside further along the chain, constructing a technological civilization that endures, building something that does not disintegrate or fall silent before anything else in the neighborhood has an opportunity to register its existence. That word, building, keeps returning in this investigation. and recent findings about how life itself gets assembled suggest that the pathway to biology may be wider and more navigable than previously understood, which only intensifies the difficulty of accounting for the silence at the far end of that pathway. For decades, the dominant explanation for the origin of life on Earth was the RNA world hypothesis. The idea was appealing in its simplicity. Ribonucleic acid, a long-chain molecule that can both preserve genetic information and catalyze chemical reactions, somehow self-assembled from available raw materials in Earth's primordial chemistry. Once it existed, it could replicate. Copies introduced errors. Errors that happened to improve replication fidelity were retained. Natural selection, operating at the molecular scale, proceeded from there. Eventually, over millions of years, RNA-based systems discovered proteins, which were more capable at performing metabolic chemistry, and then DNA, which stored genetic information more stably. Life in this account began with a single class of molecule finding itself in the right chemical environment at the right moment in geological time. The RNA world was appealing because it resolved biology's fundamental chicken and egg problem. Proteins require DNA for their synthesis instructions. DNA requires proteins for its maintenance. RNA can perform both functions inadequately but sufficiently, making it the plausible origin point. Research published between 2023 and 2025 substantially revised this picture. Multiple independent studies showed that amino acids, the precursor molecules of proteins, and RNA nucleotides, the building blocks of RNA, likely co-evolved from the earliest stages of prebiotic chemistry on Earth. They did not emerge sequentially, one precursor class preceding the other. They appeared simultaneously, interacting in ways that rendered both molecular families more chemically stable and more functionally capable than either would have been in isolation. Peptide RNA interactions, meaning short amino acid chains physically associating with RNA strands, propelled the emergence of primitive genetic coding through two discrete stages. The first stage was purely chemical. Amino acids and nucleotides assembled cooperative molecular networks in which each component stabilized the other against chemical degradation. The second stage was informational. Those cooperative networks began encoding and transmitting rudimentary chemical instructions to daughter molecules, the remote ancestor of the genetic code operating in every living cell on Earth today. Think of the conceptual difference this way. The RNA world model is equivalent to saying a vehicle was constructed by first building a flawless engine, then attaching wheels, then adding a frame. The coevolution model says the engine and frame and all remaining components emerged together, each component making the others possible. Life was not one molecule getting fortunate. It was a network of molecules lifting itself into existence. The distinction matters profoundly for the Fermi paradox. If the RNA world hypothesis were correct, abiogenesis depended on one specific molecule achieving one specific chemical configuration under one specific set of environmental conditions. A tightrope walk over an abyss. If the coevolution model is correct, abiogenesis resembles a highway with multiple lanes and multiple entrance ramps. More chemical pathways lead to living systems. The transition is more robust and more tolerant of environmental variation. Every revision to the origin of life narrative over the past 3 years has made biology appear easier to initiate, more chemically probable, more likely to occur wherever environmental parameters permit it. And every such revision has made the silence more difficult to account for. Because if the road from chemistry to life is a highway, and the universe has had 13.6 billion years to travel it, the total absence of traffic at the destination demands an explanation that chemistry alone cannot furnish. Something is halting the progression after it begins. Something intervenes between the emergence of biology and the emergence of a detectable signal. The question is what? And a researcher who studies economics proposed an answer that reduces the problem to pure geometry. Robin Hansen constructed the Great Filter Framework in 1996 as an economist's approach to the Fermi paradox. 3 decades later, he extended the concept into something more specific and more capable of being tested against observations. His grabby aliens model opens with a premise that sounds self-evident, but carries consequences that are not. If even a small proportion of technological civilizations elect to expand outward from their home systems, traveling at any meaningful fraction of the speed of light, they should by now be visibly reorganizing the Milky Way. Obviously and unmistakably, a single civilization advancing at 1% of light speed, roughly 6.7 million miles per hour, would saturate the entire galaxy in somewhere between 10 million and 100 million years. The Milky Way has existed for 13.6 billion years. There has been time for this to happen thousands of times over. Hansen's mathematical model projects what the galaxy should look like if expanding civilizations exist or have ever existed. They would convert stellar matter and planetary resources into megastructures on a scale detectable across thousands of light years. They would extract energy from stars in quantities that produce unmistakable infrared waste heat signatures. They would carve out territorial spheres, expanding regions of engineered space that observers could map the way cosmologists chart the large-scale structure of the universe. The model predicts a galaxy that appears at least partially constructed, with visible frontiers between competing territorial expansions extending across hundreds or thousands of light years. The actual galaxy looks nothing like that. Project Hephaistos surveyed approximately 5 million stars within 300 parsecs, searching specifically for the infrared signatures that partial Dyson spheres would produce. 7 candidates materialized. All 7 resolved to background contamination from dust-obscured galaxies billions of light years beyond the target stars. The Murchison Wide Field Array surveyed 2,800 entire galaxies at radio wavelengths for evidence of large-scale technological activity. The result was nothing. No megastructures anywhere. No expansion wavefronts, no territorial boundaries, no restructuring of any kind at any scale in any direction. The Milky Way looks precisely as a galaxy would appear if no technological civilization had ever constructed anything within it. Hansen's model offers an explanation for this state of affairs. For our own existence to be statistically coherent, for a species like ours to have evolved without being absorbed by an expanding alien civilization before we appeared, technological civilizations must be either extraordinarily rare, or they must expand extraordinarily slowly, or something terminates them before expansion begins. His calculations show that for multiple civilizations to coexist within the same galaxy without encountering each other, they would require average lifespans exceeding 280,000 years. For reference, anatomically modern humans have existed for roughly 300,000 years total, and we have possessed technology theoretically capable of interstellar travel for precisely 0 of them. The evidence from recent research makes the required lifespan appear unattainable. Garrett's 2024 model allocates civilizations roughly 200 years after developing artificial intelligence. Dugan's 2026 model grants them 500 to 1,000 years before demographic collapse makes recovery mathematically impossible. Neither comes within striking distance of the quarter-million-year threshold that Hansen's geometry demands. The conclusion is unambiguous. Civilizations do not expand because they do not survive long enough to begin expanding. They emerge, transmit briefly, and disappear. The galaxy remains exactly as empty as our observations indicate. But the investigation retains one more thread to pursue, because one instrument is still working through the last surviving candidates. In the mountains of Guizhou Province in southwestern China, a natural limestone basin contains the largest single-dish radio telescope ever built. The 500-meter aperture spherical radio telescope, known by its acronym FAST, stretches 500 meters from one edge to the other. If you placed it in lower Manhattan, it would span the distance from Wall Street to City Hall. FAST succeeded the Arecibo Observatory as the world's most sensitive radio receiver after Arecibo's platform collapsed on December 1, 2020. Its 4,400 individual aluminum panels adjust continuously in real time, providing both immense collecting area and the capacity to track celestial targets across the sky. Since July of 2025, FAST has been methodically working through a specific list. When the CD-at-Home Distributed Computing Project closed in March of 2020 after 21 years of operation, it left a legacy behind. Of 12 billion candidate signals processed by volunteer computers worldwide, approximately 100 survived every stage of automated filtering. These were the transmissions that classification software could not categorically assign to terrestrial interference, satellite contamination, or instrumental artifacts. They were anomalous enough that human analysts flagged them for re-examination with a more powerful antenna. FAST is that antenna. It is re-observing each candidate individually, directing its dish at the same celestial coordinates, tuning to the same frequencies, listening for any signal that recurs or matches the original detection characteristics. The procedure is systematic. Each target receives multiple observation sessions at different times, accounting for the possibility that a signal might be intermittent or dependent on orientation. If even one of those candidates produces a confirmed repeating detection that cannot be attributed to any terrestrial source, the framework of this entire investigation changes overnight. As of early 2026, FAST has reported nothing from any of the re-observed targets. The 100 signals that endured 21 years of distributed computation and billions of hours of volunteer processing are dissolving under the scrutiny of a more powerful instrument. Meanwhile, machine learning algorithms developed for Breakthrough Listen now process radio telescope data 600 times faster than conventional analytical methods. A data set that would have occupied a human research team for years can be screened in days. The volume of sky being systematically examined per unit of time is growing exponentially compared to even 5 years ago. The Allen Telescope Array is being upgraded to reach frequencies up to 18 gigahertz. New commensal systems are being installed on radio telescopes across 4 continents. The search has never been faster, wider in scope, or more sensitive in its minimum detectable signal. The result has not shifted. The number at the conclusion of every data pipeline remains the number it was in 1960 when Frank Drake pointed an 85-foot dish at 2 stars and registered silence. There is a version of this story in which FAST finds something genuine among the SETI at home remnants. There is a version in which the next Breakthrough Listen data release contains an anomaly that clears every verification test. Those versions are not impossible. But 65 years of consistent precedent generates a prediction about the next result, and that prediction is 0. That compels the question this investigation has been building toward since its opening lines. Not where is everybody? Fermi posed that question 76 years ago over a cafeteria meal. The question now is what the answer means for a species that is still within its own window. Begin with what the evidence has established. 65 years of organized searching, from the Project Ozma to the cosmic search on the Very Large Array. 12 billion candidates from SETI at home to 74 million narrowband hits from an interstellar interloper. Every candidate resolved to noise, to interference, or to a natural phenomenon that no one had anticipated. Every promising detection, pulsars in 1967, the WOW signal in 1977, BLC-1 in 2020, Dyson sphere candidates in 2024, dimethyl sulfide on Hey 2-18b in 2023, either definitively refuted or left unconfirmed. The pattern holds without exception. Every measurable parameter in the Drake equation has shifted in the optimistic direction since 1961. More stars carry planets. Habitable zones are more numerous than anyone projected. Life initiates more rapidly than predicted. The census of Earth-sized habitable zone worlds went from a guess to 40 billion confirmed candidates. Each revision should have made the silence less probable. Instead, each made it more statistically significant, because the expected number of civilizations kept rising while the observed number remained fixed at 0. The filters accumulate, and each one narrows the channel through which civilizations must pass. Intelligence demands a specific geological biography. Sustained plate tectonics for 500 million years or more, combined with a particular ratio of continental surface to ocean, a configuration that fewer than 0.2% of life-bearing planets appear to develop. Civilizations that reach technology face artificial intelligence within 2 centuries of their first radio transmission. Those that navigate artificial intelligence face irreversible demographic collapse within 500 to 1,000 years, as fertility rates descend below replacement and populations age past the point of recovery. The detection window during which any civilization generates electromagnetic signals powerful enough to cross interstellar distances may be as narrow as 100 years against a cosmic backdrop of 13.6 billion years. A 100-year detection window is a single water droplet falling into Lake Michigan. Thus, instruments keep disappearing. Arecibo collapsed and was never rebuilt. Big Ear was razed for a golf course. The Allen Telescope Array was mothballed for want of $1.5 million per year. Roughly 2 minutes of Pentagon spending. Congress eliminated NASA's SETI program twice. The biosignatures we trusted turned out to be less reliable than assumed. Oxygen appears without biology. Dimethyl sulfide appears without statistical confidence. In 1999, a Russian astronomer named Alexander Zaitsev used the Evpatoria planetary radar in Crimea to broadcast a targeted signal toward nearby star systems. He consulted no international authority because no binding protocol required him to. The International Academy of Astronautics maintains guidelines. They are advisory only. Anyone with access to a sufficiently powerful transmitter can announce humanity's existence to the galaxy whenever they choose. And we would not know whether anything was receiving it until a reply arrived, traveling at the speed of light, potentially decades or centuries from now. The investigation does not end with a resolution. It ends with a measurement. The universe has had 13.6 billion years and hundreds of billions of stars, and on at least one of those worlds, life appeared almost immediately and eventually produced a species that built radio telescopes and directed them at the sky, and asked where everyone else was. The silence is the answer. Something about the journey from microorganism to interstellar civilization is so difficult, so improbable, or so brief that in 13.6 billion years it has either never been completed by anything else or has never lasted long enough to leave any trace detectable by us. That is not philosophy. That is what the data reports, and it leads to one final place that is difficult to sit with. Earth has been broadcasting for roughly a century. The first radio signals powerful enough to escape the atmosphere date to the early 1920s. Military radar from the mid-20th century, peaking at around 10 to the 14th watt in directional emissions, is the most powerful signal this planet has ever produced. Those signals expand outward at the speed of light in a sphere currently about 100 light-years across, encompassing roughly 15,000 stars. A civilization operating a Green Bank-class telescope 100 meters wide, aimed at our star during the right century, could detect us. But Earth is already becoming quieter. The migration from broadcast television to streaming, from analog radio to digital compression, from omnidirectional radar to phased arrays, from open transmissions to encryption that is indistinguishable from noise. All of it is shrinking our electromagnetic footprint year by year. A civilization 1,000 years beyond us might communicate through tightly focused laser pulses or fiber networks or technologies we have not yet imagined. Their transmissions would vanish into the background. They would be invisible to us. Efficiency itself is a kind of silence. If Garrett's model is correct, the window between first radio emission and artificial intelligence consuming the civilization that generated it spans 200 years. Earth is 127 years in. If Dugan is right about demographic decline, the window extends to 500 or 1,000 years. Accept the more generous figure. 1,000 years of detectability in a galaxy 13.6 billion years old. The ratio is 1 to 13.6 million. For another civilization to detect us, it would need to exist simultaneously, within range, with instruments aimed in our direction, tuned to appropriate frequencies during our window. We would need matching conditions on our end. The probability of two civilizations overlapping in both time and space is not zero, but it is small enough on its own to account for the silence. Two fireflies blinking in a forest the dimensions of a continent. Each flash endures a fraction of a second. Each firefly is genuine. They miss each other by 100,000 years, and never know the other was there. In July 2025, the Allen Telescope Array tracked the third confirmed interstellar object through our solar system. 7¼ hours of listening. 74 million narrowband signals recorded. 211 candidates after filtering. Every one of them originated on Earth. Right now, some instrument somewhere may have swept our solar system within the past week and found what we always find when we look outward. Nothing. The silence does not establish that we are alone. It is consistent with a universe in which the windows are narrow, the distances between stars are vast, and 13.6 billion years is not enough time for brief technological flashes to overlap across a galaxy 100,000 light-years wide. The most probable outcome may be the most straightforward one. Civilizations emerge, transmit for a geological instant, and go quiet. The galaxy could be filled with ruins, or with species that are silent by physics rather than by choice. It could contain thousands of civilizations that existed millions of years apart and never shared the same sky. Any of those possibilities produces an identical observable result. 0. FAST is still listening in Guizhou. The James Webb Space Telescope is still analyzing the light of distant worlds. Breakthrough Listen is processing data 600 times faster than it could 5 years ago. The question Enrico Fermi posed over lunch in 1950 has not been answered. The instruments are more capable than at any previous moment in our history, and the window, whatever its actual duration, remains open. We are a species that has existed for the blink of a cosmic eye, built machines that can hear across light years, and turned them toward a sky that has so far returned nothing but silence. And we keep listening anyway, because the alternative is to stop asking the most important question we have ever thought to ask. Whatever the answer turns out to be, whether the silence means we are alone, or rare, or simply too early or too brief. The act of searching is the most honest thing we have ever done with the time we have been given.